sounds like she said no. All right. So I'm pretty sure we're practically at the end of this. I don't think there's much to touch up on here, but let's review real quickly. Starting, I reviewed Bohr yesterday, so I'm not going to review it again on you. But let's review basically this slide right here. Okay, the mathematical tricks when it comes to doing the quantum numbers can be helpful, especially when you don't want to think of all of the deep stuff, but also conceptually you want to understand what each of these things means. Ultimately, understanding what they mean really comes down to, maybe if I can click the button there. Understanding what they come down is really just understanding this picture, okay? Is that what, let's start off with n. What does n represent? The principal quantity, that's what it is, that's what the number is. What is it?
De Broglie wavelengths an atom has.
And I drew up on the board for you, I drew two-dimensionally what 1 de Broglie wavelength, 2, and 3 would look like in two-dimensional space, okay? The orbitals, because we're not going to worry about the math, essentially are a projection of that over to three-dimensional space. What is allowed is simply based on where the de Broglie wavelengths would have to line up in order to make the possibility of these particular shapes. You can kind of understand, for example, with 2 de Broglie wavelengths, why it would be necessary to make the P shape, for example. Okay, what would it mean? It would mean this orbital right up here would be 1 wavelength, right? What does it mean, this little space in between? There is 0% chance that an electron can be there, right? Well, could I have 1 de Broglie wavelength that would make up this shape? No, I couldn't wrap it around. I would need 0 and 0 to hit at this exact same spot. So I would need another de Broglie wavelength to wrap around this guy over here. So I would need 2 in order to make that particular shape. Same thing is true with all of the other shapes, although they get weird and mathematical and whatever. So,
so on the first one, like just the circle, is there like a 0% chance like anywhere?
Yes. I will actually show you visually that in just a second. It is actually at the center. At the very center, there is a 0% chance. As we discussed, technically, it's weird to draw this picture in this particular way. Technically, n goes on, can go infinite. So this particular shape, it's kind of weird to draw the end spot of it because there's not technically an end. It just gets low enough that it is pretty much basically 0, which we'll see in just a second. But again, mathematically, I should be able to say something to the effect of, let's go ahead and let's put that up here. Okay, let's go here. I should be able to say, if n is 1, what are my other possible options? And my other possible options with n equals 1 is, well, L has to equal from 0 to n minus 1. Well, n minus 1 is 0, so the only possible L for that particular case is 0. Okay, and ML ranges from negative L to positive L, or in this particular case, ML's only option is 0. So if n equals 1, these are the only possible states. Now, what we do then with spin, to reference spin, is we reference it in a 1/2. It either represents positive 1/2 or negative 1/2, which just is there to represent up spin and down spin. So let's just say the options are plus or minus 1/2 in that particular case. Okay? So if n equals 1, I have 2 spots for electrons because there is only one shape. There is only one possible orientation for said shape, and you can fit 2 in that particular space right there. Okay? If, let's go to another page, n equals 2. Okay? If n equals 2, I'm going to kind of write out all of the possible options from kind of left to right here. I could say n equals 2. Well, the first option is that L equals 0, because I'm going to go again from L is 0 to n minus 1. So I could go to 0. Now, if L is 0, then ML also has to be 0 because it stretches from negative L to positive L. And finally, the spin is plus or minus 1/2. So what does this say? Well, if n equals 2, I'm going to get an s orbital, there's only one orientation of the s orbital, and 2 electrons will fit in that. So this guy right here, n equals 1, L equals 0, this is the 1s orbital.
Wait, what's ML again?
ML represents the orientation of that. If you look at my picture right here, you can kind of see the representation in this case. This is S, this is P, this is D, and this is F. Okay, you'll notice just how many possible options there are for orientation. 1, 3, 5, 7. Okay, and that's kind of calculated mathematically, like I said. So this is the 1s. This whole thing is the 2s orbital right here. But like I said, n equaling 2 could have an L of 0. That's certainly a possibility. It could also have an L that is equal to 1. If L equals 1, my possible options for ML are -1, 0, or 1. Okay? And each of, actually, let's do it like this, a little bit differently. -1, 0, and 1. So if I have n equals 2, I have the other shape, possibility of P. There are 3 possible orientations for P, and all of those orientations can have an ms of plus or minus 1/2. So how many possible electrons can we fit inside this guy right here? Well, there's only one shape. 3 different orientations. Each orientation fits 2 for a total of 6. So this whole block right here represents 2p. And yes, and we can fit 6 in that particular spot. Now, yes, let's go ahead and move. Sorry, actually, I think Trent was really go ahead.
Why is like ML negative then 0 then positive? Where does the negative significance of the negatives come from? Why is it just 1, 2, 3?
This might be an ignorance thing. Okay, I believe it's so that they can give a simple mathematic explanation of it.
Why there's no number that?
Yeah, essentially, it's a very quick way to go. Like, okay, now we can. I know that for I think that it would be harder to create an equation. I think with other particular sets of numbers. I believe. I could be wrong on that. That would take a little bit more research. Yes.
Where does the 1/2 for spin come from? Is it always?
Why is it 1/2 versus some other
Is it like
number?
always 1/2?
I don't know the answer to that. I don't. I apologize. I don't know. Why don't they just use -1 or +1? Or?
I mean, like, because L is defined by like being -1 in from like 0,
Mhm.
and like ML is defined by L. So is MS like always?
Always plus or minus 1. 1/2, rather. Sorry. The way that you show it, like I said, there's other ways of doing the kind of the electron configurations that we did yesterday. Rather than write, well, I mean, you saw me do this yesterday, so I'm not going to spend a bunch of time on it. But so this represents the set of numbers that we had on the other page. I'll go ahead and put that up here. N equals 1, L has to equal 0, ML has to equal 0, and MS is equal to plus or minus 1/2. This is, of course, like we said before, the 1s orbital. So rather than write them all out, this is another way to do it, and you represent the spin, in which case you draw an arrow up and an arrow down in that particular case. And you fill each suborbital, meaning the S, 1s, 2s, first. But actually, if you come over to P, like let's say we had, I think it would be nitrogen. Nope. Yeah, nitrogen was 7 up there. You don't fill this one first. You actually go like that, and that would be the correct orbital notation for a low electron configuration. Yeah. So why is it plus or minus 1/2? I don't know why it's 1/2. But plus or minus is to represent up spin and down spin. As I mentioned the other day, spin represents very similar to angular momentum. Spin is also a direct reasoning for what we discussed in magnetism, that magnetism is created by moving charge. Well, if you remember, the only magnets that are only elements out there can naturally create magnetism is iron, cobalt, and nickel. And if you look at those particular sections right there in the heart of it, specifically I'm thinking iron, 1, 2, 3, 4, 5, 6, you get essentially, and I'm not sure why magnesium doesn't fit in there. Or is that manganese? I can't remember. Yeah, no, I think it's manganese. Anyway, but essentially there's 4 electrons that are all up. They're all spinning the exact same way, not uncountered on the other side. So that's why you kind of look at the currents that are created by those electrons going those particular spinning thus particular ways, and thus the reasoning for magnetism. Good. You had a question for a second? Or, okay, never mind. All right. So the point of this whole conversation is to talk about the mathematical numbers that you can certainly use, but also trying to understand, again, what they are. And what are they? Once again, N is the number of de Broglie wavelengths. L represents the possible shapes that you can make out of that number of de Broglie wavelengths. And so again, this picture probably right here is best suited for that. N equals 1, the only possible shape is S. Okay, N equals 2, the only possible shapes are P or S. Okay, N equals 3, now you've got these 3, 4, you get the general idea. I could keep going down the line. And as I showed you yesterday on that particular chart, the reason that we don't worry about the particular shape of the G orbital, suborbital, which definitely does exist, is that it is not going to be necessary for the lowest energy state. Even those guys right up there, we can get to 7s over there with francium and radium, but we do not. I think what is that? The F is across the bottom right there. F is it's got 14 in it there, and which sublayers are those? That is 4. Yeah, that is 4F and 5F. Am I right on that? Yeah, 4F and 5F are those bottom two. So we just have 4 and 5F. The D layers that we have there are, the top, as we saw yesterday, was 3, then 4, then 5, and then you'll notice kind of how late my periodic table is right there, because across the bottom right there does not have the same across the bottom as what yours has. And if you want the most up-to-date one, let's go to the online periodic table that is updated regularly. You can see how far we've made it so far on the periodic table. There you go. Yeah. So we have made it actually all the way over to the, here is, 3, 4, 5, 6, 6, and so now we've actually made it over to the 2, 3, 4, 5, 6, 7th P layer. We've actually made it to the P layer right here. Now, why do we probably not expect to go further? Well, right down here it says the elements with no stable isotopes, the mass number of the isotope is just the longest half-life in parentheses. These are existing for fractions of fractions of fractions of fractions of seconds. So it's very unlikely that we would need them. Yes?
Oh, okay. Never mind. I'm just looking at the equations that they gave.
This, like I mentioned yesterday, is an excellent resource. Obviously, I want you guys to be able to create these on your own. But if you're home and you're like, and obviously I'm not around and I can't check or whatever, and you're like, but Spainhour, how do I figure out what the orientation is for, say, like yesterday? I think what did I do? I said say iron. Did I say iron yesterday? Boom. Look at this really cool thing right here. It fills 1s1 and 1s2, and it kind of positions these correctly distributed so that you can see that that the p where is it at? That the p orbital of 3, sorry, or what is it? 4d is a little bit higher than 3d is a little bit higher than 4s. That 4s is in a lower energy state than this guy right over here. You can also, if you want to see it entirely written out, boom, there it is. And then the actual shorthand version, right there. So that's a good resource if you're stuck on this stuff. Okay. Principal quantum number is 5. How many values of L are possible? 5. 5. Remember that for L, you also have to like then think of the 0 as well. You're right, the highest value of L is 4. The options are 0, 1, 2, 3, and 4. Principal quantum numbers N. How many different values of ML are possible?
Oh, 5. 9.
11.
You're gonna want to think deeper about that.
11.
They're all the same number.
So they're not meaning anything but the same thing.
ML would be the possible amount of orientations there. So yeah, yours in that particular case is going to be 9. Why 9?
Because it's the negative.
So, well, also on top of that, you go. I'm struggling with ML. I'm missing this up in my head. L possible options are 5, but for 0 you get 1, right? For 1 you get 3. So 4 for 2. I feel like I'm doing this right.
I think it's just asking like the negative.
1, 2, 3, and 4, 1 blue and 2.
You know, possible MLs are possible for N equals 5.
Well, I thought that you used the equation that it gave you. It said 2L plus 1.
These are out of order, I feel like. Oh, okay. I see what they're doing for it. Yeah, 9 in that case, because they are. That's a weird way to say that. That is a super weird way to say that, because it is not okay. Here's what. Okay, they're fine, but I still think it's dumb. How many different values of L are there? So yes, so they're not repeating, but that's really dumb. So here's what I thought they were asking, and quite frankly, I think that's a dumb question. I would not ask that. This is what I thought they were asking, which I think is a better question. What is distinct values of L and ML are there? And that's the one I was doing. That's the one that is 25. Because, here we go, if N equals 5, the first option is for L is 0. How many possible MLs are there? 1. So now you go, okay, now N is 5. The next possible option is 1. How many possible ML values are there? 3 for a total of 4. Now we go to L equals 2. How many possible options are there? 5. So now we're at 5 in, so we're at 9 over here. Okay. Next possible option is 3. How many possible options are there? 7. So now we're 16. And finally, last possible option is 4. How many options are there? 9. 9 into 16 would be your 25. Yeah. Yeah. This one is weird as we're talking about. All right, that's spin. All right. Electron clouds. This is probably the best depiction of essentially what this thing is, what this orbital thing is that we're talking about. Now, you'll remember that I talked roughly about de Broglie wavelengths and that it's not quite what the cloud is. The cloud is a probability wave, which is actually related to the the wave function squared. And the wave function was actually a squaring of the de Broglie wavelength. And the reason why you're getting multiple squares and things in there is due to the fact that you are dealing with 3-dimensional space and not 2-dimensional space. But essentially, here's the s orbital represented over here. This is probably the best representation of the s orbital, because while it kind of appears like it has a definite end to it, it kind of like fades and fades and fades and fades. And to represent this, what you're looking at right here, okay, what you're looking at right here for the hydrogen, for S, is the probability with respect to R from the center. So you'll remember the other day we calculated that the lowest radius of hydrogen at A0 was 5.29 times 10 to the negative 11th, or 5.029 nanometers. You'll notice that's right here. That is not where the electron is. That's where the electron is most probably to be. Now, sadly, most probably does not mean it's at 98%. It means it's probably like 50, 60% likely to be in that particular spot. As you head towards the center, you'll notice that it gets less and less and less and less, and it is actually 0 when R equals 0. And like I was talking about, this is why I kind of struggle with kind of the definitive edges. Obviously, you have to draw a picture that way, but just conceptually, is that if you come over here, you'll notice the probability doesn't ever actually reach back to 0. It just gets smaller and smaller and smaller and smaller, and actually kind of has an asymptote right there. But we would treat it as stopping at a spot where you're looking at it relative to the rest of it. It's pretty darn close to 0 in that particular case. questions, concerns about this. So this is actually, if it helps, actually not this entire thing. This is the two-dimensional graph of probability versus R if you start at the center and go out that way along the x, or technically any of the directions, but we'll just pick that one direction for, yeah.
Is this just for the x-orbital?
That's just for the x orbital. Yes.
This probability of being at that radius from the center.
Mm-hmm.
So it could also be closer than we said it was supposed to be, but less.
Well, that's and yes, and that's why
Probability of it being closer.
that's why when we made Bohr's model, this dotted line that I'm drawing right here is that radius, is a 0. But then let's go 3 spots here. Actually, let's go 6 spots. Then I drew this. To represent 3 de Broglie wavelengths in this particular orbit. So what does it mean that these are kind of like bigger or smaller? Well, this means that this area is more probable than this area over here. And you'll notice that there is space. It could be over further away, and it could certainly be closer. That particular spot.
So it can fall anywhere within.
Yeah. And actually, I can make those de Broglie values bigger because technically you could stretch all the way, as you just saw a second ago, almost to the center of the circle itself. It just cannot be at the center. All right. Ooh, how are we feeling?
So the graph represents the probability of where an electron, or where like the electron would be
In two-dimensional space. So if you look at this picture, the graph basically, this corner starts right here and says it's a 0% chance of being here. And then if I go this way, basically pick an axis because all of this would be exactly the same. But if you want to say, instead of R, you could say X as you head out along the X, it's going to be most probable like right here at a 0, and then get less and less and less further away. Okay.
What is the wave function?
The wave function is the actual probability. So the relationship, I'm kind of going back and forth very quickly between a de Broglie wavelength and a wave function. And it is a complex switch that I'm not super worried about, okay? Because for the most part in our understanding, they're kind of the same thing. The wave function is, we talked about this at the end of 27, but just for a moment, so. Where is it at? Right here. In 1926, Austrian-German physicist Erwin Schrödinger, if you guys have heard of Schrödinger's cat, this is essentially his baby was the wave function. Okay, the Austrian-German physicist Erwin Schrödinger proposed the wave equation that describes how matter exchanges in space and time. Schrödinger's wave equation represented a key element in the theory of quantum mechanics, and is important to quantum mechanics as Newton's laws are in classical mechanics. In Schrödinger's equation has been successfully applied to the hydrogen atom and many other microscopic systems. Solving Schrödinger's equation is well beyond the level of this course, and that is an understatement, and determines a quantity called the wave function, denoted by the Greek letter phi. Each particle representing a wave function phi is both dependent on position and time. Once phi is found, phi squared gives us the information on the probability per unit volume of applying this particle to a given region. To understand this, we turn with Young's experiment involving coherent light passing through the double slit. First, recall that the intensity of the light beam is proportional to the square of the electric field associated with said beam. According to the wave model of light, there are certain points on the viewing screen where the net electric field is 0, resulting in destructive interference from the two slits. Because E is 0, all those points, intensity is also going to be 0, and the screen is dark there. Likewise, at points on the screen where constructive interference occurs, E is large, intensity, blah, blah, blah. Now consider the exact same experiment when light is viewed as having particle nature, the number of photons reaching, blah, 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 I don't know how to get into this. Essentially, and this is probably a gross simplification, but it'll work for our purposes at least right now. De Broglie wavelength is kind of like a one-dimensional probability to a certain degree, and the wave function gets into volume and three-dimensional space, essentially, of what it is, and that is a little bit of a simplification. But for our purposes, what we need to understand is that the wave function is the actual thing. That is the actual probability of where something is. And the de Broglie wavelength essentially kind of understands how to get to that particular wave function. There was what's up?
What are like the units on it?
Oh, existence per unit. I don't know. I don't remember off the top of my head. I took this class in college. It was a class called Waves, in which we started in very basic simple harmonic motion that you guys did last year, and ended with Schrodinger's equation and trying to do the math and breaking our brains in half in order to do it. So it's been a minute since I've done it. I'm sure that honestly you could probably look it up online just as fast as I could, and that's probably where I have to go to find out. All right. Do what? The inverse square root of length. That's unhelpful. All right.
Oh, that's the unit.
So, exclusion principle in a nutshell. Okay. I talked to you guys. You guys are used to SPD and F. What you're probably not as used to is the major shell. Okay. Because the major shell is usually just associated with the number of de Broglie wavelengths. That's n. But you'll notice right down here, n equals 1. They actually all have letters associated with the overall shell, k. So essentially, if you will, k represents the entire amount of possibilities. So how many electrons fit in if n equals 1, how many possible wavelengths, how many possible electrons fit in there? 2. So that's why the subshell k will have an n value, would have a amount of 2. Okay. Now within each of these big shells, there are the subshells. These are the ones that you're used to. So to understand this, if n equals 2, the big subshell is called L. It's not super important that you understand that, just to know where these letters are coming from. Okay, and then the possible options for L are both S and P. These subshells fit inside of L. Since 2 will fit in S and 6 fit in P, in the big shell of L, you can fit 8 electrons. And this is, of course, what you're probably the most used to because you're at the periodic table within chemistry and you regularly, like I said, most chemistry teachers, when teaching sophomore level chemistry students, don't worry about the in-depth nature of all of this particular level. Usually what they go is, let's stick in the first 20. Let's stick in the first 20 mostly so I don't have to get to the 3D subshell and talk about that weird conversation, because to have that weird conversation, we've got to talk about the probability function. We have to talk about energy and what energy truly actually is as the probability of an object being at a particular location, blah, 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 blah. Let's not worry about that right now. I don't know. I do not know the answer to that question. So that being said, like I said, k is n equals 1. You got 2. L, you could fit an S or a P. You get 2 and 6. You get a total of 8. N is 3. And while these are not, let me be very clear, these are not just rows. Actually, the first 2 rows do match nicely, but the next one doesn't, because the third subshell takes sodium and magnesium there. There's your 3s. And then, of course, you can go over to aluminum, over to argon. There's your 3p. But as we discussed yesterday, actually the 3d is, what is it? Yeah, scandium. Scandium all the way over to zinc is over. No, that's not true, because one of the, no, that is right. That is right. The D hasn't messed up because it doesn't get to F yet. Yeah, so you get a total of 18 that fit in n equals 3. And then if you want to go to n equals 4, well, now you can get S and P and D and F. So you get 2 plus 6 plus 10 plus 14 for a total of 32 possible electrons that fit in that major shell. But when you usually write them, we don't even worry about the major shells because we're writing the subshells anyway. All right. Click, click, click. If you want, this is in your book. I think it's actually in a table in the back of the book as well. This is the ground state configurations of everything up to kryptonite at 36. So Boom. If there's any answers that you're looking at and you're like, I don't know, the answer is this. I told you that you could look on, I forgot this was here. So you can look on the table, or you can look everything through 36 is already on there. One thing to point out with this particular guy, though, is the ionization energies. Okay, the amount of energy that it takes to take an electron from its lowest energy state and remove it from a shell. And this is, of course, the ionization energy to move an electron. Why is it hard to move an electron out of hydrogen? Well, hydrogen and proton are very darn close. Okay, why is it harder to move one out of helium? Well, helium has 2 protons. And when you consider the electrons going around helium, you don't worry about 2 of them separately. You worry about these 2 protons are holding on to this electron, and these 2 protons are holding on to that electron. And they're holding on sort of twice as well, because there's 2 of them. So it makes sense. The ionization is almost twice as much in that particular case. Why does lithium get so much easier to remove the electron for? Well, this is just chemistry conversations. What's that? What did you say? What were you going to say? Were you going to say the answer? Oh, fair enough. Okay. Well, the other thing is that yeah, you've got 3 electrons. Well, 2 of those absolutely fit in the 1s1 orbital. But where's the third one got to go? The third one, as we've said, is like 4 times further away. So yes, your protons, you've only got 1, 2, and 3. Now you got 3 times the amount of protons that a hydrogen did, but the distance is 4 times further. And if you'll remember that whole equation thing of Coulomb's law, the distance matters by a factor of a squared. So now this electron is so ridiculously far away, even though these have 3 times the amount of protons as before, is it going to hold on to them very well? Nope. So it's pretty darn easy. So humor me with this. Why has beryllium got a higher ionization energy? Just one right up. It's just right here. So I got more protons, has more force. It's going to hold on a little bit better in that particular case. What's that?
Removing the second electron harder is another thing. Like once you get through the first one, it's harder to remove the second one after that.
Yeah, absolutely. And you'll notice that as we go up and up and up, ionization energy goes up and up and up and up. Now you might comment on the fact that, wait a minute, fluorine I thought was the most electronegative. Why on earth does it have such a high number? Well, the ionization energy would be the energy to remove electrons. Does fluorine regularly remove all 7 of its electrons in order to get back down to? Absolutely not. What it does do is it gains another electron because it's got a huge freaking nucleus and it only needs 1 more to complete its outer shell. All right, moving on past that and properties of elements in that particular case. That's a whole chemistry conversation. This is what I talked about at the beginning. This is just Mendeleev doing his thing from 1834 to 1907, lived 2 years beyond when Einstein wrote his particular paper. So I believe Mendeleev did in fact meet Einstein. He was old at the time, but old for that particular time. He was only, I say old, he was what, 66? He would have been 71, 73 when he passed. So he met Einstein. Okay, and yeah, so he was positioning them according to their properties. And boom, you get this guy right here showing the, showing the same stuff that we were talking about yesterday. This is all that same sort of jazz as before. You'll notice that the alkali metals, the most important thing about the alkali metals, this first thing, is that they get 1 electron in their outer shell, and that's why you guys having fun. You guys get things knocked out over there. Cool. All right, almost done. Okay, you'll remember this from I think it was the last chapter, and I told you that we would talk about these characteristic X-rays specifically as before. When metal is bombarded by high-energy electrons, a metal will regularly emit X-rays. X-rays typically occur of a broad, continuous band and a series of intense strips that are characteristic of the type of metal used for its particular target, as shown in figure above. These discrete lines, called characteristic X-rays, were discovered in 1908, but their origin remains unexplained until the details of the atomic structure were developed. When high-energy electrons collide with an electron in the inner shell of a target atom, it can sometimes impart enough energy to remove electrons from the atom. A vacancy is then created in that shell. In other words, when you look at the n equals 1, it is possible with a really high energy electron to have so much come along that basically, even though you've got like a full shell, the one on the bottom of the shell, because they teleport, is the one that skips out because that's the one with the appropriate level frequency. Meaning, if I had a low base level of -10, okay, and then I had, say, like -3 and -1 and -1/2, if a photon comes by, with an energy of 10, none of these other level skips are kind of possible. You can't go from 2 to 3 or 2 to 4 with this 10. The only thing you can do is go from 1 to skipping entirely out of that particular process. When that happens, there is an empty spot underneath. Well, what are these electrons above going to most likely do? Fall down. And when they fall down from 2 to 1 or from 3 to 1, this is the cause of these two particular spikes at these particular locations on that guy right there. All right. Briefly going over this guy right here. So characteristic X-rays, this is just looking at, we can estimate the energy of an emitted X-ray, considering 2 electrons in the K shell of an atom, whose atomic number is Z. Each electron partially shields the other ones, so Ze, so each is subject to its effective nuclear charge. And so essentially you can get the energy as just Z, the atomic element, -1, squared, just kind of like we normally do, Z squared, times that guy right there to get the amount of energy coming off of that particular value. Characteristic X-rays, I'm not going to worry about that right now. Let's talk about lasers for half a second. All right, I think this is it, and then I'm done. Lasers are weird. Okay, so what you're looking at is the atomic transition lines. Okay, you have essentially, once again, like we discussed before, you have a photon coming in with HF. That frequency has a very specific energy, and that very specific energy is the difference between 1 and 2. This, of course, will cause an electron to jump from E1 up to E2. And you see the electron going from its ground state to the excited E2 in this particular case. Okay, now this, oh shoot, I'm trying to remember the exact names they have for this because the names can be helpful in separating what the situation is. And Jackson did choose a bad set of days to not be here.
Is he sick or is he just not here?
I have not told anyone that. Okay, yes, here we go. So in that diagram, that is known as, if you want to write this down, stimulated absorption process. At ordinary temperatures, most atoms in the sample are going to be in a ground state. A vast majority of them are. If a vessel containing many atoms of gas is illuminated with a light beam containing all possible photon frequencies, so a continuous spectrum like one coming from the sun, then only photons with these certain energy levels, the difference between E1 to E2, E1 to E3, E1 to E4, or 2 to 3, 2 to 4, 3 to 4, any of those possible options, and so on, can be absorbed. So atoms are raised to various allowed energy high-level states. So this electron on the far right side there is said to be in an excited state. All right, now, the first most natural thing that you would expect to happen, okay, is in a certain amount of time, which we discussed yesterday, the fact that the electron will fall from 2 to 1 is also weirdly a different probability. The likelihood that it can happen at sort of any amounts of time, but there's kind of a standard average, as it were. When it falls down, it will emit that photon. Now a laser by itself, you go, okay, the whole purpose of a laser is to get more of those photons out. But as the process we've just described, you go like, why is there a gas there at all? Because all we just did is put a photon, absorb it, and then essentially just get rid of the exact same photon. So why is there an element there at all if we want to make more photons out of a laser? Currently, what we've just done is put one in, it went away, and then we got one out, right? So we could just have the same number of photons starting from the very beginning, okay? Typically, an atom will only remain in an excited state for an average of times 10 to the -8 seconds, or 10 nanoseconds. It's not much time. The laser part comes out of this next one, which is weird. So, the third process that is important. The first process was stimulated absorption. The second process that we just got done saying is spontaneous emission. This is what we've already talked about in here. Electron jumps up, that's absorbed. Electron falls back down, it lets go of the same photon that just came into it a second ago. The third process is called stimulated emission and was predicted by Einstein in 1917. Suppose an electron is in excited state of E2, like you see in the first picture. And the photon with an energy of HF is incident on it. So, meaning, okay, so starting from the beginning, here's an electron in the lowest energy state. I got a photon with the right amount of energy, and it's jumped up, okay? Now, this is a second photon. The second photon that's coming along here, okay, is of this exact same energy difference. But there's no way to make that jump. It's already in a higher energy state. Yes? So this is a second photon that comes through here. I told you a second ago that a photon will be emitted in roughly times 10 to the negative 8 seconds. What has been found is that incoming photons will increase the probability that the excited atom will return to the ground state and emit a second photon having that exact same amount of energy. So now you've got two identical photons resulting from stimulated emission. The incident photon, the one that came in, and the emitted photon that's the exact same phase as the incident photon. Basically meaning you get two photons sort of out of one in this particular process. So you take an amount of gas, you put that gas specifically in here, such that that gas, as we saw in the back, will have very specific energy 1 and energy 2 states. You then hook up a voltage source that only has a very specific amount of energy, such that it'll take it up to E2 and start to fall back down. You put that energy in here, essentially, you put those photons in, and this process starts happening. And then there are mirrors on both sides, so that the photons you just emitted come right back and kind of basically build in this particular process until they accidentally come out the center, and you get, of course, I don't need to do battery on this. But you get the general gist of it, idea. There it is. That is essentially how all lasers, there we go, it's probably our best option. That is how all lasers are made. So how do I make a laser with a different color? Different gas.
And different energy.
Which is why you might notice that lasers really only come in 3 common colors. And those are red, green, and blue. Why? Because those are the gases that we have the most prevailing amount of, that we can easily get and put into something, and this thing costs like $5 maybe, because of the prevalence of that particular gas. We could use other gases and we could get other lasers, but they are certainly a lot more expensive. And you can make different lasers out of different gases, but that's a whole process and a whole actually industry on top of that to see what properties there are of different lasers and how much they can do. And of course, then you can get lasers that cut eyes, holes in eyes, and then you can get optic surgery and all that sort of thing. All right.
Nobody online knows what gas creates the color pink.
There might not be one. Oh, that's what it's from.
Like, when you get like
A lot of different lights and filter out the ones that you need until you have pink.
Certainly could. I mean, that happens all the time. I mean, that's what you see with like lights at like a show.
Apparently
Well,
this
not
is-
quite. They don't use lasers in that case. White light and then filters.
Okay, this YouTube.
All right,
video-
I'm done.
Okay.
Oh, I have a question.
The rest of the time is going to be spent on homework. What's up, Jay?
If like electrons just have a probability of being somewhere and like aren't really physically moving, how do they have a velocity to make like a magnetic field?
It's an excellent question, and it goes back to where's it at? The correspondence principle. Quantum mechanics is an agreement of classical physics when the energy difference between the quantized levels is very, very, very small. So essentially, we can treat these particles of things going by as though they are a particle. You can kind of think of it like this. Okay, I could make a you can think of a particle of electron sort of like a pulse wave. So here I go, I've got a string, I put a pulse in. Can I give a velocity to that particular wave? Yeah, I can absolutely see the velocity of that wave. It covers distance in a certain amount of time. And if my hand is over here and that wave hits, is there going to be a force incident on it? Yeah. So here's my electron with the de Broglie wavelength. Can it have a velocity? Can it incident force and energy as though it's making contact with things? Yeah, the exact same way. I'm sorry. But the good news is that what that means to you, and this is why chemistry does this all the time, and why I teach it this way, is you talk about what's actually going on, but all of this kind of approximation goes, and we did this with relativity as well, goes, yeah, but you can treat everything entirely like normal within a particular set of conditions, and that particular set of conditions is most of the time. Meaning, okay, so here's special relativity. Do I have to worry about special relativity when I calculate how fast my car is going? No, not unless you want to worry about 25 significant digits. And I'm going to go ahead and say NASA uses like 3 or 4. I think you're okay doing a little bit less than 25. Do I have to, for an electron, traveling in space, is it actually a particle? No. Will it interact and pretend as though it is a tiny little particle that acts exactly like a little cue ball that I've always seen it to be? Yes. Do I have to go back to thermodynamics and think about what it means to be at temperature and all of those molecules bouncing around and go, holy crap, those molecules aren't in fact entirely there. Well, luckily they're at low enough speeds as well as acting independently themselves, they're going to act exactly like tiny little cue balls bouncing off of each other, even though they are these particular packets. So yes, they are not an actual particle, but none of the math really changes that much, even if you treat them as a particle in that particular example. So should you know what it is? Absolutely. Do you have to change the way you view kind of like all of the other maths then? No, not really. Last thing before I answer any of your questions here real quick, because I want to put this on the video before I stop here real quick. You guys have heard of Schrodinger's cat, yes? Yes. The example of Schrodinger's cat, by the way, was a hypothetical that he gave that I actually think is bad that he used a physical object because people get confused by it. Schrodinger's cat was, again, completely hypothetical. He was trying to explain to people essentially what he was doing with the wave function, and what the wave function means, and how observation changes that particular situation. So what he said was, the idea is, by the way, Einstein used, Schrodinger used gas. I think Einstein uses explosives, so I like Einstein's a little bit better. But basically what he said was, okay, that the cat is in a box. You cannot see the box, okay? Inside the box there is a vial of poisonous gas that has a 50% chance that it is going to explode and kill the cat. The cat is not currently, it was trying to get people to say, is that the cat, and this was explaining the wave function and what a particle of electron actually is. The cat is not alive or dead. The cat is in a superposition. It is both alive and dead. And what he then said was the act of observation, us opening the thing and looking at the cat, is weirdly what decides. Now, that feels super weird because in your head you go, that doesn't make sense. The cat is alive. Whether or not I know or not, the cat is alive or dead. So here is Spanauer's version of the Schrodinger cat that I think fits a lot better. It makes more sense to talk about this probability function as something you're very used to, probability. It's when a teacher looks at an entire class and starts using probabilities to discuss what's potentially going to happen to you in the future. I've done it myself for particular reasons, but it's kind of crap. When I look at a class and I say, all right, guys, currently the graduation rates at particular colleges throughout the United States are like 40%. That is to imply to you sort of that you have a 40% chance of graduating. To which you go, well, that's not fair. I am my own person. Stats are all of these people collectively. I am not 40%. I am either, yes, 100% success, or you cannot be 40% successful because of all of these stats, right? And that stat, while it might apply to a big whole, does not apply to you individually. You are not 40%. You are not one way or the other. It doesn't matter until you actually go to college, and then the actions that you take will either make you 100% successful or 100% unsuccessful, right? So you can kind of think of the 40% sort of like a probability function for all of people, just like the probability function is sort of for like all of these electrons. And it is the process of observing, or you going to college, that will decide whether or not, yes, you are successful, or no, you aren't. There is no, until you observe it, you are not both. You have currently, as far as time understands right now, you have currently not graduated college and graduated college, because both possible outcomes are likely, equally, or not equally as likely, in the future. If you put that statistic to it, they would say it's slightly more likely that you're unsuccessful, but you are not either until you actually go to college. Yes? That's the idea that they're trying to get to with the electron. The electron's probability, the electron is not there. The electron is not anything until you actively observe it, and then it does have a definitive outcome specifically where it's at. That's what Schrodinger's was attempting to explain with his particular situation, although most people misconstrue it because, one, they think actual cats died in the example, and number two, they struggle with the idea of, okay, that 50% the cat's dead or alive, object permanence means whether or not I look inside there, it is one of those things, and that's not what he's trying to say. He's trying to say, imagine that you saw the cat as equally as likely. Anyway, all right, I am done.